So ETEC 214, we're going to look a little bit at problem 1 from week 8. And a couple weeks ago we looked at pumped air storage. We went over the ideal gas law a little bit, showed that, well, we looked at PV equals nRT and decided that pressure is actually energy per unit volume. So once you multiply pressure times volume, you get energy. This week, we're looking at pumped hydro. Something I just learned recently through a latest forum and through the latest news coming out of California is that California wants to have 1.3 gigawatts of storage by 2017, 2018, something like that. And so my question was, what do you mean by watts of storage? Because we get back to that watts. Well, what it means is that, like right now, whatever storage system or systems you have can suck up energy that quickly. It's almost like a capacitor versus a battery. You would have one big giant capacitor ready to suck in all those electrons as fast as you can hit it versus a battery which you can only charge so fast. So 1.3 gigawatts in California in a few years.
I don't think they can use pump storage. They're all out of water.
And the environmentalist won't let them.
They could put it where the aquifers used to be.
What I'm surprised is they haven't greenlit any desalination. Like why don't they have like 10 plants?
Yeah, well, you know, so with the ocean, it seems like you could just pump ocean water up and down.
Put big old solar.
Actually built the desalination plant. Now they're figuring out how much it's going to cost. They never ran it after they built it. So they're figuring out how much it's going to cost them to start it back up for 30 years.
Oh, really?
Yeah.
Where in California was this?
It's somewhere in the Bay Area.
Because they need about 10 of them just to pump water back into their aquifers.
Oh, I did some neat notes last night. Let's.
Or they need superstorm from the 1860s. Rained for like 40 days straight. The water was like 8 feet deep in downtown Sacramento.
It would need, like, those reservoirs are at like 2%.
That whole valley that Sacramento's in, that entire valley was like several feet deep. And it was several hundred miles across. It looked like an ocean. You couldn't see the other side of it. Couldn't see the other shore. Like 1863.
They definitely need big old PV arrays out there that, and then your desalinations only run when you're getting like wind or solar.
That's exactly the way to do it. Just run the big heavy machines when you got extra juice. I think that's run your cardboard shredders, run your desalinators, run your hot water heaters. Just store the waste energy. Love it. Okay, so again, best place to start on this is just with some of the physics. So what's our potential energy equation? NRGY 101. E equals what for potential energy? MC squared? No.
Mass
Let's store this in a nuclear reaction. Say again?
Mass times height.
Yeah, MGH. Another way you could also think of weight times height. Mass times gravity is the same as weight. There's your height, but in this case, mass times gravity times height. We're running this on Earth, so gravity's not changing. We're just going to keep that as 10 meters per second squared. Where's the mass coming from in a pumped water storage? Just the water going uphill, right? So we're basically looking at 4 different segments of power in this system. And what I'm going to do, I'm just going to call this one the power of the water, and that's kind of your physics. Right here is the power of the pump. This guy right here is the power of the belt, and this is the power of the motor. And it's a little tricky, a little bit weird, because you've got, I'll do one more, power of the electricity, right? So electric power is flowing in the motor, mechanical power is flowing from the motor into the belt, mechanical power is flowing from the belt to the pump, and then the pump is pushing that water uphill. Yeah. So, I just got done telling you, well, and here's another few ways to think of it. Power equals IV, right? That's our electric. I told you a little while ago that power equals force times velocity, small v. In this case, what are we looking at for hydropower? Again, you're always going to have an across variable and a through
You need
variable.
the head.
You need the head. What is the head equivalent to? Is it equivalent, and maybe I'll write these a little bit.
Height. Energy.
There you go. Yeah, perfect. I'm going to write it like this. P equals V for voltage times I for current. So, there you go. So I'm going to write the H first. And I'll just write big H. I wrote a big H. Okay, so voltage, force, and height are sort of equivalent in that they are all the across variables. And what's this guy going to be here?
So are we looking for the power? So you want flow.
Yeah, exactly. Flow.
So you want the density of the water, gravity, head, velocity, and area, right?
Yeah, that's right. And they all end up going into the mass flow rate. So, and again, and this is a perfect way to start thinking about power. So it's volts times amps, it's force times velocity, it's also head, it's the same as pressure, times the flow rate. Gallons per minute, cubic feet per second, liters per hour, whatever, some volume per unit time. So let's first calculate that guy. What's the head in this case?
The head is,
I think it's 60 feet in this case.
60 times.
Well, 60 feet is actually the head. Now, we got to take 60 feet and turn it into PSI. What's the physics behind that?
Is this one? Because it says 60 PSI.
It's the other way around.
Oh, I'm sorry, 60 PSI, thanks. Same difference. Okay, how do we turn head into PSI? How do you think about that guy? Pounds per square inch. So here's how I like to think about it. Just keep it small, human scale. Let's just take a square inch tube. I'm kind of thinking like a Pringles container, but a little smaller. Just imagine little mini Pringles that are an inch, like Cheez-Its. Cheez-Its stacked in a little square. So it's a 1 inch by 1 inch square. 1 inch by 1 inch. Now, we're just going to start filling with water until we get 1 pound, right? Because that's 1 pound per square inch. How tall is that Cheez-Its box of water when it weighs 1 pound? Okay. I just heard 2.3 feet. Did you calculate that, or did you just find it somewhere online, or did you?
I'm on an engineering toolbox.
Yeah, so it's out there. It's 2.3 feet. If you had, let's just say you're out offline, at some point, you got to memorize something, right? I mean, atmospheric pressure, density of water. You could go back. You're going to have some table with you, but let me show you what I ended up doing here. Let me show you what I ended up doing. This guy, 213, 215. Of course, it's 214. Week 8, pumped hydro. think I just used this guy. Oh, pounds per cubic inch. So a cubic foot of water, so imagine a suitcase of water, a cubic foot, 62 pounds. Pounds per cubic inch, much smaller, 3 times 10 to the minus fifth. Look what I ended up doing here. Yeah, okay, yeah. So I went on to Engineering Toolbox, found 2.3 as the height, went to make sure that it was about correct, and calculated what the volume in cubic feet is of something that's 2.3 feet high by 1 inch by 1 inch. So to do that, I just imagined that I need 144 of those things to make a square foot. So I divided 2.3 by 144, came up with that number, and then I went in, multiplied that volume, so it's 15 thousandths of a cubic foot, multiplied that volume by the density of water, which is 62 pounds per cubic feet, and I got approximately 1. That much water weighs 1 pound. Okay, so that's where that comes from. So from there, somebody read the equation to me from the assignment. Power of the water.
The WHP equals gallons per minute
GPM.
times feet times specific gravity over 3960.
Okay. Now, the specific gravity, what's the specific gravity of water? One what? Yeah, so the specific gravity of water, it equals 1 because the specific gravity is defined by water. And it's really just the density. It's a density ratio. So the specific gravity of oil, if it's 80% as dense as water, specific gravity of oil is just 0.8. If a chunk of concrete is 5 times more dense, its specific gravity is 5. So that's where that comes from. The 3960 is just a combination of all of these numbers, GPMs to feet to et cetera. And what's this power in? Is it horsepower, watts? What's it rated in? Water horsepower. Okay. Equals water horsepower, and it's measured in HP. Okay, so we're dealing in conventional units. So to get that, what are the numbers? Just how many gallons per minute? 3,000, right? 3,000. And if you convert, so I'm just going to take our 60 PSI, and I'm going to multiply that by, well, let's just do it this way, multiply that by 2.3. I'm going to multiply that by 1, and I'm going to divide the whole thing by 3960 equals, now let's hop out here. Okay, so there's my 60. I converted it right there. I used probably more significant digits than I needed to, but I converted that into head in feet. So we're actually pumping this thing up 140 feet, 138 feet. And this guy, all I did was run that little equation, so my head and feet, gallons per minute, times 1. Don't have to bother multiplying by 1, but there's specific gravity, and then divided by 3,900. If you wanted to get a little more sophisticated, if the temperature of the water changes, hot water is a little less dense, you're not going to be pumping as much if you're doing as many gallons per minute, but that's splitting hairs. We'll just leave it at 1 for now. Okay, so Water horsepower, 105. So right there, we're looking at 105. And again, that's just getting the stuff to move uphill. Now, other things that we're given, the efficiency of the pump, so we'll write that as eta sub P equals 0.7. The efficiency of the belt, efficiency of the 0.96. Efficiency of the motor,
92.
0.92. Okay, is the power of the electricity going to be greater or less than 105 horsepower?
Yes.
Careful, careful. You're going to need more juice.
I
yeah.
thought we were getting power from, no, we want to pump something up.
Yeah. Right. So each one of these little efficiencies or inefficiencies, if you will, is going to take a little tax on our system down the way. So we know right off the bat, let me write my 105 in here. We know right off the bat that PE is going to be greater than our 105 horsepower. So, and that's something you should just do right from the outset, because once you go through your Excel and screw it up 2 or 3 times and you come up with PE equals 5 horsepower, you know you're wrong. There's your sanity check on your Excel.
My bad.
So pump power, and again, I mean, the same is true coming upstream. We also know that, and we could just even write it like this. We've got an equation almost set up. We know that the pump power is going to be greater than the water power. We know that the belt power is going to be greater than the pump power. We know that the motor power is going to be greater than the belt power, and we know the electrical is going to be greater than the motor. So, to get the pump power, all we're doing is dividing by that efficiency. Same thing on the belt power, dividing by that efficiency. And I'll just give the disclaimer, my Excel spreadsheet here is not in its final good-looking form. I'm just kind of going through it as I did it last night. The motor power, again, we're dividing by its efficiency. And then finally, we get up to the true motor power. Now, we had a little discussion last night about whether we're measuring apparent power or true power in that motor. And I'll let you guys dig around on that one a little bit. I'm not going to get too crazy, but I do want to show where the power factor equation comes from. And maybe that's a good question for the forum. Good question for Al Frazier, whether the power going into that motor is true or apparent. Because apparent is volts times amps, and the reason that the apparent power is different. I know I'm going kind of fast here, but let's look at it.
Wouldn't that be the apparent because it's an unknown, we're extrapolating it based on efficiencies?
Maybe.
I would think it would be apparent because we've only calculated it, we don't know.
Yeah, well, let's leave it as a question for now. I'm just not 100%. So we got one vote for apparent, we got one vote for true. Let's see if we can figure it out. But here's the way to think, again, just to go back and look at the reason why true power, apparent power, and reactive power are all different. And Tim, just chime in too and help me out here if I'm going. So what's happening, and again, it's the voltage that's shoving the current through the motor, right? So here's your voltage, your sine wave coming in. Here's your voltage sine wave coming in. Now I'm going to pick a different color. So, and, a good way to think about this too might be, I was thinking a good way to do it would be a tug of war. I'm gonna pull on the rope. The actual rope moving is gonna happen after it gets pulled on. So there's your force. And then later, since you've got all that copper you're pushing the electrons through, later comes your current. So there's your I. Now, what ends up happening is these two guys are out of phase by some angle, and let's just call it phi for phase angle. If they were exactly in phase with each other, if that red line were right on top of that black line, phi would be 0. But they're not. The longer that wire, the more they're going to be out of phase. Now, and again, we can kind of get back to our phasor diagrams, and you can think of your voltage as kind of pushing now in that direction to the right. Not that voltage has a direction, but and then your current, okay, comes along a little later. And there's your phase angle. So and this is I over here. So the hypotenuse of that triangle is equivalent is analogous to the apparent power. Let me draw another one. This guy on the bottom is going to be your true power. This guy right here is your reactive power. Because in a lot of ways, the current is reacting to the voltage. And then this hypotenuse is your apparent power. So, Pythagorean theorem. Apparent power squared equals true power squared plus reactive power squared. And the power factor is true power over apparent power. Also happens to be equal to the cosine of that phase angle. So far, so good? The question we need to figure out here is if whether we're dealing with apparent power or true power come into that.
That wasn't given on the assignment though, right? Power factor is 85%.
Yep. Yeah, power factor is given. What we were struggling with though is the power flowing through the motor the true power or the apparent power? We're not sure which of those two we're actually given. If we're given one, we can calculate the other. The question is, were we given the numerator or the denominator in that particular case? That's the main struggle, question, what have you. And so what I did, and again, it might be wrong, I took the motor horsepower, just multiplied it by our 0.746 to get what I'm calling the motor true power. Could be the apparent, again, just still a little shaky on that one. But from that, here's your motor power factor. Obviously, the motor apparent factor is going to be greater, right? So if we go back here, cosine's always less than 1, so big number on the bottom, small number on the top. And then from there, I threw in Pythagorean theorem. So this guy, you can see, is no more than reactive power equals square root AP squared minus TP squared. And I can do it the other way too. Let's just do it the other way in case this is not correct.
Be cosine the power factor of the motor times your motor in kilowatts.
Yeah.
So we need to do the Pythagorean theorem to figure out the reactive cost?
That's just how I did it. You know, if you want to figure out what that cos theta is, so another way to do it would be to do theta equals cosine minus 1 of the power factor equals cosine minus 1 of 0.85. So we can run that. We actually get what theta is. So let's do that. So here, I'll just do this off the side. So power factor. And again, power factor is always going to be something between 0 and 1. It's a little bit like an efficiency, 0.85. So here's going to be cosine minus 1 PF equals, and the term in Excel is A cosine, arc cosine, 0.85. That's the arc cosine in radians. I'll throw that out there too, cos minus 1 in radians. And a better way to write that arc cosine is to take that negative 1, hit it with a control 1. Wake up, Bill Gates, there you are, superscript. There it is in radians, and now we take that, copy it, paste it, enter. Now we can get that guy in degrees. Equals that degrees of that in radians. Throw a control 1 at that guy again. Number. So this is phi, and you can put a F and then home SYMBOL. So your phase angle's 31.79 degrees, 32 degrees. So you wouldn't have to use the Pythagorean theorem. You could say that you could also come in and go RP over TP equals tan of phi. If you want to go to the trouble of calculating tan of phi.
So you have 78 kilowatts for reactive power on your spreadsheet. So I just got that by the water horsepower times kilowatts per horsepower.
You could also calculate the amount of reactive energy. Is that even a term?
Reactive energy. I guess you could. I mean, if
A
you
bar that gets produced by
I guess you could, if you just added up all that reactive power.
The horsepower, well, you figure out how many kilowatt hours, or how many kilowatts the engine has based off of horsepower. So if you find the reactive power based off of horsepower, then it all should equal the same thing, right?
There's like 4 different ways to do that equation to get that K bar.
Yeah. How'd you get it again? Dustin?
The water horsepower, which was 105,
Yeah.
times 0.746 kilowatts per horsepower. I didn't know I was finding reactive power though, so.
Did it just work out that way?
Kilowatts is what I was doing.
Wait.
Yeah, I think you should redo it, yeah.
That sounds a little, that sounds a little bit like 1 to 12 roof pitch equals 12 degrees to me.
Well, it looked like 12 degrees, man.
I know it did, but at some point you're gonna get lucky. I'm just.
I swear, I'm gonna find this reactive.
That's another way to do it too. Tangent, ACOS, your power factor, your 0.85, times this, whatever this total is, times your true power
Okay.
of 127 kilowatts.
Let's
Will give you the same,
let's shoot that guy
the
up.
same as Brad's equation that was the square root.
Yeah.
Is this reactive power, Tim, on the right? Is that what-
Let's see.
I just
Um,
Is that where you're going with it? Reactive power
Yeah, this will
equals?
give you the K bar, based on, it'll give you your peak reactive energy, and that is your 85 PF, that's your 85 or 0.85,
Yep.
5%.
Yep.
And that's your 127 kilowatts.
Yeah. true.
78.33 kilowatts.
And it gives you 78.5, which probably based on rounding, because the one you did was
Yeah.
the square root.
Yeah.
So
This,
just a little round.
yeah, so what Tim just wrote on the board here, reactive power equals tan of the arc cosine of the power factor times the true power are my two equations combined. That's all that is, yeah.
Why wouldn't you have mentioned this type of math at all? Like,
Oh, I'll tell you why not, because it's covered in 213. That's why
Oh, yeah.
I could totally take the derivative of that right now.
Go, man, go. Chain rule?
Oh, yeah.
You have a little chain rule with that?
Yeah.
Yeah, and this, so, for what it's worth, I'm glad I'm going through this right now, because a couple of years ago, there was an administrative decision made to put 213 and 214 in the same semester. But now I'm seeing the error in that, because,
Not good.
no. 213 really needs to happen. I mean, all this needs to happen in the fall in 213, and then you should be able to hit the ground running with this stuff in
And the stuff that you're
214.
covering in 214.
Yeah.
You haven't got to yet in 213.
Yeah, so, it's, I'll take the blame for it. It was, when this stuff was set up, Brian Kearns and Tom Gallagher were running the show, and I think Paul Williams was still in charge, and I think it was put together pretty well, and they're like, "Okay, Layden, here's the team of horses." I'm like, okay, what's your name? But here's how to look at this thing. So is that as clear as can be?
Yeah.
Okay. So, and again, where I was going to go with that was to say, just going to call this motor apparent power 2. I'm going to call this one motor true power 2. So another way to run that. Here's the motor power. I went straight from that into motor true power by using the conversion from horsepower to kilowatts. Second way to do it, if we're not dealing with, if we're actually paying for apparent power and not for true power, because that's a big if, you could run it this way, equals motor power times 0.746. And now
Divide that by 1,000 as you're using a decimal.
no, we're good here. True power. True power equals apparent power times power factor. Equals apparent power times. So in the first scenario, so your apparent power is always going to be greater than or equal to your true power. So in the first scenario, I calculated a true power of 127, came back with an apparent power of 149, bigger. In the second scenario, I calculated an apparent power of 127, came back with a true power of 108. One of those is correct, the other one is not. Good forum question. Okay, so let's continue on. I'm going to assume that the first case was correct. So I calculated my motor reactive power as the square root of apparent power squared minus true power squared. Came up with 78. Obviously, you're going to get a different answer if you run your scenario 2. It's going to be smaller triangle. Hours per year, we got it at 6,000. You're paying 3 separate charges here. You're paying for how many kilowatt hours you ran. You're paying for the demand cost, for how long you were over, what's the threshold on the kilowatts? If you're over 300 kilowatts? No. We're not under the kilowatt ceiling, are we? Let's go back.
So the demand cost is $6 per kilowatt month. Reactive cost is 28 cents per kVAR month.
$6 per kilowatt month. Oh, so it's not a ceiling. So here's your $6. So again, I just use the motor true power to get to the demand. I just multiply the number of kilowatts by your $6. So in that case, you're just kind of paying for the size of the tube the electricity's coming down, not the size and the duration. I think I did that right. Then I came up with a demand cost. I just multiplied the per month by 12. That's the annual. And then the third thing you're paying for is the peak reactive cost per kVAR. And that's 28 cents. And I just did it on an annual basis. I came up with 78 kVAR. And that's, one way to think of it is kilowatts. Another one way to think of it is kilovolts amps, which in a lot of ways is more accurate because of these little triangles we've been dealing with. Your volts and your current are out of phase, so your true power and your reactive power are out of phase. And that's the number I came up with. And again,
No, it shouldn't, you got an extra number in there on that one. What was your formula for?
What?
For your reactive cost? It should be, so C25, that's your.
it's my power.
8 cents,
Yeah.
okay. That should be times your 78,
Yeah.
C19.
Oh, and then just time-
Oh, because you,
I multiplied it by the hours. Is that?
no, because that's, because you're just gonna, because that'll give you your monthly.
Oh, okay. That seemed low to me, though. Is that all it is?
Yeah, it's only $263.
Ah, okay. It did seem like a lot for just the kVAR.
Yeah, yeah. So it should be those two multiplied
So,
time, without the, instead of the 6,000, it's just 12 months.
well, there we go.
There you go. That looks-
And then, and I've got my annual built in with the
Yep.
12. Okay. That seems more reasonable, thanks.
Wally can answer our question on the 213 transformer question.
The safety?
No, what was the, if you're missing one leg of the
Yeah,
transformer?
I think that was, the safety one, yeah.
You're missing one leg of your
And
transformer.
a startup,
Of your control transformer. Yeah, here's the question. Sure you
Sometimes
do.
contact
Put the
people
prop
at
on
5
this.
degrees flat
Oh.
install. It would make 47,000
Control transformer
500
or
kilowatt
across-the-line three-phase motor starters tested found to have an open
Yeah,
and secondary line.
hill.
Discuss what would occur if an attempt were made to temporarily operate the control system directly from
So
two
that equates to,
of the three-phase power
yeah,
supply.
so 10 and a half.
It would just be on the two that were in place would be,
I don't know, we'll just have to see what the braces cost to raise that.
so if it's splitting it, right, you got a
Loading.
secondary line or three-phase
It's so much
motor.
better to do.
Just what would occur if there were.
Right.
You got the answers?
No.
When I'm thinking about this,